Welcome back, everybody. This is a bit of a divergence. This is a build video of, well, a part that I made for my airplane that I couldn't find to purchase anywhere. I hope if you find it interesting, let me know. Thanks for watching.
Okay, welcome back to another installment of Peter's working on his airplane, or whatever I've called this YouTube thing. Okay. One of the things that I am doing is I'm creating I was looking for I was looking for some kind of a device that I can hook up to my fuses, as well as to my EFIS and my engine monitoring and my fuel level and all these things, so I can have warning lights on my panel. We see it all the time. I think I've mentioned this before in a different video. And I think I also mentioned that I couldn't find anything, and I've designed one for myself. It went through 4 different, prototypes and iterations until I finally got it right. And the final board, looks like this. That's the final finished product. There's the back side. And got a bunch of components in there, and a bunch of components on the front side, and a bunch of dip switches. And now what the dip switches do is it allows me to select what kind of an input I'm providing it. Is the input one that goes low, meaning it flows and goes to negative when it goes into alarm, which is probably the most common out there. Is it an input that goes high when it goes in alarm? You find those as well. Or is it a steady voltage, like for a fuse, that if the fuse blows or the breaker pops and the voltage drops, that's when you get an alarm output. So with these dip switches, you can select each input separately. Now here's a mock. Here's the one of the boards I've got set up for it. Already wired up. It's got a little beeper inside here and all that, and it's got these illuminated lights. These are all LED lights, and a red alarm push button. And so let's say the EFIS alarm is triggered. Well, what happens? Well, quite simply, let's just cause it to trigger. Oh, hang on. Works better when you actually select the type of input on the dip switch. They're all turned off, which means no alarms can happen. Which is also an option that if you don't, if you're not using all 10 inputs, you just leave them turned off and they're inactive. So here we go. There you go. The alarm clears because the EFIS alarm is now cleared. Now let's just say, for example, I'm going to switch this. No, actually I'll do it this way. So watch the EFIS alarm. I hope you can see that. It says EFIS alarm and the red push button. And I'm going to give it an input to trip the alarm. And I'm going to hold it there. Now notice the alarm did not extinguish. I silenced it, but it's still there. That's telling me that the EFIS is still in an alarm condition, and all I've done is silence the sounder. Now, the sounder I've got on here right now is just a high-pitched, simple piezo sounder. I'm trying to locate something to go into my airplane that's loud enough for me to hear, or I might actually design an audio output that gives me in my headphones an audible tone that goes off. So instead of having a piezo sounder or some sort of external buzzer, which I might still have, so if you don't have your headphones on, you'll hear it. But if you put the headphones on, you might not hear this. So I'll probably have 2 things going off. One is the sounder that's external, and then an audio that's injected into the intercom system that says, that you've got an alarm. So as you can see right now, the EFIS, this says EFIS alarm, it's still in alarm, and hopefully you can see that. Here, let me turn this light off for a second. There we go. It's nice and orange, and the red master caution is still lit until I remove the alarm condition, and when I press the master caution again, it extinguishes. It means the alarm's clear. Now, I decided to design it that way on purpose to latch in alarm, because if you get something that goes off momentarily, and you're looking out the window like you should be, and you go, oh, look, and then you hear the beep beep in your headphones, and you look down, says and it's okay, you had an alarm, but it's gone now. Well, I didn't want that. I wanted it that if it went into alarm, and that was a momentary trigger. There we go. That was a momentary trigger. It's still showing me that the EFIS went into alarm, and when I hit the master, it extinguishes, tells me, oh, okay, it went in and out. But at least it stays on until I acknowledge it. Some people might say, hey, I just want it to go off when it goes off. Okay, well, there's a way to do that as well. The way you wire up the switches that it self-resets. But I'm going to do it so that it doesn't self-reset. I'm going to do it so that it latches. So anyways, that's what I've got here, and this is the actually, this is no longer work. This is not a prototype. Actually, this is the one that's going to be going into my airplane, and I have another one here. It's exactly the same, and it's been tested. And I have a couple more boards here that I'm going to be building. Well, I actually got 3 of them, and I have enough parts to populate 2 more, well, 2.5. Yeah, so I'm going to assemble. Let me turn this light back on. There we go. I'm going to be assembling 2 more of these, and then with the using my reflow oven, which is blowing behind you right now, and I'll record this. I'm not sure if you're going to find it interesting. I'll probably fast forward through a lot of it. Put this on high speed once I start actually picking and placing components, because that's going to take a little while, and you don't need to sit there and watch me for half an hour or more putting tiny pieces onto a circuit board. And yeah, they are tiny pieces. It's all surface mount, and just to give you an indication of that, these little silver domes, they're capacitors. But these, let's say these 3 black things on the side, you can see my finger side, those are transistors. Okay? And beside those transistors, those are resistors. So, yeah, they're very small. But they're not the smallest you can get. Oh, no, no, no. These are actually humongous. They're big compared to other ones. Yeah, I went surface mount because I can make it smaller. If I went through the whole conventional, I could design it that way, but the board would be like 4 or 5 times bigger, and I didn't want that. I wanted something really, really small, and but big enough that I can still work with it. You know, there's a human factor involved. So yeah, that's I'm going to be making 2 more, and because there are a few guys in the flying club that saying, hey, I could really use that for my experimental. So so I'm going to make 2 more. I've got 2, one for me and one for a group that I'm with that we're also building another airplane. So I'm a part owner in that experimental, and so I'm building. Well, actually, that's what this board is for. It's going to be the alarm panel on that aircraft, and then I'm going to be building 2 more, and maybe 3 more. Then I'll have to order them parts, and for some other guys who'd like them. So yeah, it's that's what this is. Now, just to let you know, there's no software involved. This is 100% analog. It's all just transistors and resistors and diodes and capacitors. It's just discrete components. There's no software. It's not like an Arduino or a Raspberry Pi or something like that you need to program. This is 100% analog. So there's absolutely zero chance of erasing software and not having an alarm. This is either going to work or it's not going to work. And I've burnt in this. Here, let me turn the power supply off. There, a little quieter. I've done some burn-in tests with this particular unit where I had it in an alarm condition, all 10 inputs in an alarm condition, lighting up 10 lights, and a small load on there to simulate a buzzer, and I let it run for 7 days to see, is it going to burn out? No, it didn't burn out. And then I tried, creating the alarm and leaving it in alarm condition, like pulling it lower, pulling it high, and all. And so it actually went through about 2.5 weeks of torture testing, and then ramped up the voltage, dropped the voltage, and all that kind of stuff to simulate, well, will it handle 17-volt spikes? Yeah, it does. The transistors I've used and the components, actually it's mainly me and the transistors. Transistors I've used are really forgiving. This will operate down as low as 6 volts and as high as about 17. Now, if somebody's got a 24-volt system in their aircraft, I can easily design a buck converter. I wouldn't use a voltage regulator. They're very inefficient and they draw a lot of heat, so I'd use a buck converter instead because they run much cooler and much more efficient. And when I put this in a box, I can put that buck converter in it as well, and then you can feed it anywhere from 6 to, say, 35 volts, and it'll work. It'll be happy with whatever voltage. Plus, I've got reverse polarity protection on this as well, because hey, people sometimes mix up the black and the red, because like, which one goes where? Which is a positive? So you need to build in reverse polarity protection if other people are going to use it. Originally, I wasn't, because it was just for me. But when other people said, hey, I kind of like that, so I said, okay, that's where the other redesign came in. So, okay, reverse polarity protection came in. But it's still 12 volts. And so if somebody starts saying, hey, I need something for 24, then I'll build a little cheap buck converter for that as well and put it in the box. Now, this is going to be going in a box. It's actually a pretty big box that'll house this circuit board. Plenty of room in there. Okay, and there's a battery died. I'm not exactly sure where I left off. I guess I'll start with this box. It's going to go inside of a box like this. And I made it this large for a couple reasons, and that's because you might stack a second one on top of it in case you had more than 10 alarm inputs. Like if you have, say, 14 fuses and you want to monitor all 14 individually and indicate, you can indicate them all as, under one light that says fuse, but you might have 14 fuses and each fuse requires its own input. You can't strap the two of them together. It doesn't work that way. So yeah, this is stackable inside here. And also I figured the connectors, I was going to use screw terminals, and I thought, nah, you know what? Everything in this industry, in the aircraft industry, looks like everybody's going towards the or is using the 25 or 9-pin or 15-pin D-sub connectors, and that's what I'm going to do. I'm going to just put 25-pin connectors on here and label them so that you know what are the inputs, what are the outputs, and where's the power and all that kind of stuff. So then you'll get a box that you need to hook up to your lights and to your push button, and you know which wire goes where. And it was designed specifically to work with LED lights. It will run incandescents, but your power draw is going to be massive compared to LED. So I ran LED lights instead, so that they're extremely low current draw. And because last thing you want to do is just add a power pig to your aircraft. It needs to be efficient. So that's it. It's going to go into this box. So what I'm going to do here is build two more, and this is going to be into a really fast, super speedy Gonzalez, or can I even say that anymore? The Flash. Yeah, there you go. It'll be sped up a lot because it's me picking and placing and stuff. So, alrighty. So follow along. We'll build two more annunciators.
All right, well, that ends the explanation of what I am building, or what I have built. Now we're going to go into me building two more of those boards. It's going to be greatly sped up, massively trimmed. There's almost 3.5 hours of video that is going to be compressed down to a few minutes by using a warp speed. So sit back, relax, and enjoy. I will be narrating this warp speed section. Thanks a lot.
What follows is a brief construction montage.
Well, hope you get your seatbelts fastened because it's going to be warp speed. Now, the little syringe that I just spread on that stainless steel plate has solder paste on it, and that stainless steel plate has tiny, tiny microscopic holes in it. Well, they're actually not microscopic, but they're tiny holes that line up exactly with the solder pads where components get laid. Now, you notice when I lift up that stainless steel, there's other circuit boards there. They're just used to hold the board in place so that they line up properly with the holes in that stainless steel plate. So I squeeze solder through it, and a tiny amount of solder, just the right amount, gets laid down onto that circuit board. And now you see me peeling off components, the right components, and looking at that piece of paper, and okay, which component goes where, and using tiny tweezers, I am placing these components. You do need a steady hand, and you got to make sure you don't sneeze. If you sneeze, you will literally blow the components off that board. Actually, that's a static-free mat. And yeah, forget trying to hunt them. They're gone. They're dust. So yeah, that's me moving at really, really fast speed. I'm sure that people would wish I worked that fast all the time, but they don't. All right, so yeah, it's essentially a slow process. The back side of the board in real time took about 40 minutes or so to place, 40 to 45 minutes to spread the solder and place the components. And remember, the back side has maybe 10% of the components that the front side has. The front side or top side of the board has the majority of the components. And yeah, so here we're going to be going into a cut, or no, we're not going into a cut. I'm watching the video on the little tape thing on my editing software to tell me when things happen. So yeah, not much more to say over here. This is just me putting more components down. So rather than listening to me ramble, maybe I'll tell a joke. Nah, maybe I won't tell a joke. Maybe I'll just edit this out. Okay, well, you'll know in a few seconds.
We hope you enjoyed this brief construction montage.
Okay, hopefully I'm in frame here. That was the sped up version of me putting components onto the circuit board. Now I need to bake it. Yes, just like baking a cake. Only this is a little different. This is what's called a Reflow oven. It's a homemade version, and it's actually a kit that I purchased. And yeah, you buy the toaster oven, you buy the kit with the controllers and all that kind of stuff, and you put insulation inside of it all around, and an extra heating element and temperature probes and all that stuff. Anyway, so what it does is it melts the solder. And now that all the components are in place, I simply place them there, close the door, and go to Profiles, run a profile. Oh, hang on. Oh, oh. Choose a profile first. Okay, I'm using a lead paste solder. That's correct. Run a profile. Okay, so now it's because the solder paste I'm using is lead based. I This will run lead base, of course, and silver solder as well. The lead base solder has a much lower melting temperature and is safer for certain components. And since I am using these plastic dip switches, I chose to go with lead-based solder because I don't want to melt the dip switches. Now it says it'll handle it, but it's so close that this is a much better option. So, am I recording? Yes, I am. Good. Right now it's warming up. It's currently 34 Celsius, 35, 36 Celsius in the oven. It's heating up quickly, and it will bake. So, yeah, that's the back side of the circuit board. Now, you may have been seeing me looking up this sheet here. This is my schematic diagram. Actually, no, it's not a schematic. It's a pictorial because this is showing me the traces and the component layout. And then, of course, I write in pen what the value of certain components are. And this, then when I look at the circuit board, I know which component to pick and where to put them. So this is for the back side of the board. And this is for the front side of the board, which has got considerably more components in it, as you can see. So we're done the back side. I can put this away. And after this bakes and cools, I will start populating the front side of the board and make 2 more of them. So, and then I will count my components and see how many I've got left and what I need to order in order to make that last one. I ordered 5 circuit boards as prototype boards and made 2 of them and put one through massive torture testing. And then I tested the second one, went through all its paces, and it proved good. So, yeah, I have 3 more circuit boards. I'm making 2 more. But I don't think I have quite enough components to make the last one because I was doing some more prototyping on something else and I was using some VITS components, so whatever. Yeah, so we're at 113 degrees Celsius. It is pre-soaking the circuit board, and what that simply means is that it's warming up the solder paste. The solder paste has flux built into it. This is almost empty. I got to get some more. I should have enough to do the front of these 2, but I got to order another batch. So this solder paste has flux already in it, and what it's doing right now is it's evaporating the liquid from the flux, and it's doing it slowly. You don't want it to boil. You don't want it to bubble, because if it bubbles, it'll lift the component off the circuit board. And then what happens is what's called tombstoning, where you get these little components. It'll just flip right up and stand up on its end, and then it'll solder itself in that position. It's called tombstoning. And in order to prevent that, you've got to pre-soak the board slowly to bring it up to a certain temperature, which dries out the flux in the solder paste, yet the components stay attached, and then it ramps up the heat quickly, melts the solder, and through surface tension it'll realign most of the components so that they sit back where they should be, and then it soaks it for about maybe 30 seconds at its high temperature, and then it turns the heat off, and this little solenoid here moves and it opens up the door a little bit, and that starts the cooling process. You don't want to cool it too fast because then you're going to get cracks in your solder possibly, but the cool down is pretty quick. You can handle the boards after about 10 minutes or so. It takes it up to 220 degrees Celsius. I'm not sure what that is in Fahrenheit. It's a lot. Because water boils at 100 Celsius, so that's more than double the temperature to boil water. But there we go. We're at 156 degrees, and We got 3.5 more minutes. Oh, no, I'm sorry, that's not quite right. We are into it for 3 minutes and 45 seconds. In the soak phase. When it reaches 165 degrees Celsius in the soak phase, right now it's 161. When it reaches 165, it'll hit all the elements and ramp it up quickly so that it exposes the components to the least amount of time to the high temperature as possible. So, oh, reflow boost coming in 8 seconds, 7, ooh, it's counting down. So we will see this go into, yeah, there we go. Now it's going into its boost phase. I'm not sure if you can see that on the camera. I'll find out when I'm editing. If you can see this graph line here, it's going to start picking up really quick. And it's rising in temperature. Now when you first set this oven up, and when you build it, you run through a couple of tests, and you where it learns how fast it heats up and how fast it cools down. So it knows that in 25 seconds I should be at my peak temperature and shutting it down. Because right now we're 19 seconds into it, we're 196 degrees, 197, 198 degrees. Yeah, when we hit that 220 target, which should be, according to this, in about 7 seconds. Now there's a little bit of smoke coming out of here. That's from the glues, the glue and stuff when I built this. It still hasn't fully baked in yet. I've only ran this about maybe 9 or 10 times since I've built it. Before that, I used to use this Reflow hot air to melt everything else, and it was a real pain. This Reflow oven is much, much better. Okay, we are at our target temperature. The elements have turned off. It's just soaking. 10 more seconds, and then you'll see the door open. And all the solder should have been melted, and everything's all in place. And their cooling phase. There we go. See the little motor turning? Yeah, a little bit of smoke coming out. Oh well. That's from all the glue. So that's it. And you can see this temperature thing is just, ooh, it's down to 177 degrees. It's dropping pretty quickly. When it goes below 100 Celsius, then it considers it cooled down properly, or safely anyways. That's boiling. I wouldn't touch it, you know, not yet. I'll take them out with needle nose, but I'm going to leave them sitting aside there for a bit. Actually, when it hits that that timer that says it's at 100 Celsius, I'm going to open the door all the way, let it cool down a little quicker. So that's it. That's the back side of the circuit board. I'm going to film me picking and placing on the front side of the circuit board in case you guys are interested. Now I'm going to fast forward through that as well. I'm going to see how quickly I can do that in the editing process to zip through so it looks like I'm going to be like Superman, or I might even actually cut out sections and edit it down so that you're not watching me do that for more than a minute or two or so, or 3, whatever, until so you get the idea of what I'm doing. So yeah, these are the components, the sizes of the components. Again, for comparison, there's my finger, and each one of those little black squares is a resistor, and that's my index finger. Here, I'll give my pinky finger. It's how many can I fit on my pinky? A lot. And that's an 0805 package. That's a large package, or it's considered large. So yeah, so that's a resistor. As compared to, here's a 1/4 watt resistor. The conventional size of a 1/4 watt resistor. Oh, come on, get up there. There, that's a conventional 1/4 watt. That's a very small resistor compared to a surface mount. So it's, you know, you can fit about 2 of them side by side, and then of course you have the wires to deal with. And this one, so yeah. All right. Just waiting for it to reach 100 degrees. Okay, you know what? I'll be back.
2 very boring minutes later.
Okay, we're at warp speed again, and right now I am inspecting the boards looking for tombstoned components. Seeing none, I decided to go on and do the other side of the board, and there we go. I'm going to do the top of the board now, spreading solder paste at this warp speed, and I start laying components. Now, this is actually about a 2-hour process, but from start to finish. Obviously, I've cut it all out because there's no point in me having you watch this for 2 hours straight. I don't think anybody would want to watch that. So anyways, this is greatly sped up, and I'm going to slow it back down again before I put it into the reflow oven, because I do explain one of the things I do when I do double-sided boards. So, back to normal speed. Hope you enjoy.
Okay, the top of the board is now fully populated with components. All I need to do now is to put them in the tray and bake them. Now, I don't know if I have to do this, but I don't like laying the other components flat on the hot surface. So what I do is I use these little stainless steel nuts, and I position them strategically so that they keep the circuit board just off of the surface. Again, like I said, I don't know if I need to do that, but I want to do that, so I'm doing that. And that should be about right. Run profile. Let it paste. There we go. One more time, and we'll see. I'll probably fast forward through this, but yeah, that's how you make the circuit boards that will annunciate trouble conditions in the airplane. So we're going to let that go, and we'll be back.
As you can see, I'm checking the boards once again, make sure everything is A-OK, which it is, so I'm happy.
I'm rambling. It's late. It's about midnight, and I'm done. I'm baked. And my circuit boards are baked, and they're nice and cool now. Cool to the touch. That's nice. So there we go. That's the controller for the lights.
A few moments later.
That's it for today. Thanks a lot for coming along. Hope this wasn't too boring. Me working on electronics, you know. It's the geek in me. What can I say? Everybody has their inner geek, and this is where my inner geek lives. Is here in this workshop, as you can see, or at least this area, my ham shack. So take care, and make sure to like and subscribe. Hit that little button on the bottom there, and tell your friends, you know, hey, watch that crazy guy that's working on his airplane, but he also does some electronics stuff. So and hopefully we'll see you again. Once again, thanks a lot. I appreciate you watching. Keep your stick on the ice. So long.
Sorry, no blooper reel. Just the closing out. Thanks for watching. I appreciate every one of you. Bye-bye.